Oh, hi. I'd like to spend a few minutes with you talking about the quantum numbers and our ultimate goal. And our ultimate goal is up on the board, and that is, where are the electrons? So let me hold up a little sphere here and tell you that it might represent a helium atom. And we know that helium, being one of the Nobel gases in group 8 or 18, is extremely inert. The reason that helium's inert is because of its electrons and where those electrons are, how many of them. So we'd like to find out where the electrons are to answer the questions like, why is helium inert? The O2 molecule, the oxygen molecule, is extremely reactive. We live by it. We go ahead and breathe it, exhale carbon dioxide and water. But this also aids us. Oxygen's extremely reactive. It's because of its location and how many electrons that there are inside this molecule. So we'd like to answer the question, where are the electrons? The water molecule, nice little model here, HOH, H2O is bent. And the reason that it's not linear, like in a straight line, but it's actually bent, is because there are a pair of electrons up here and a pair of electrons up here, and it's making these hydrogens bend down because these are actually pairs of electrons. These wood sticks are representing pairs of electrons. And it turns out that because water is bent, it's extremely special. It has some great properties. If water were linear, the world as we know it would be quite a bit different. The boiling and melting points of water would be different, and our lives would be different. Xenon. Xenon's one of the noble gases, element 54. And I'm holding up a little bit larger sphere next to the helium. And xenon's been made to react, even though it's a noble gas. Doesn't like to, but we can force it to react. Something about where the electrons are. So we'd like to answer the question, where are the electrons? We use quantum numbers and quantum mechanics to go ahead and tell us where the electrons are. To begin with, we'll start with one of the 4 quantum numbers. We often call it the principal quantum number. We use lowercase n, principal quantum number, and n tells us the distance from the nucleus we find electrons. And while quantum mechanics is not definite, so it's not telling us exactly where we can find the electrons, it is giving us a probability function. So I can say things like, hey, 95% of the time we would expect to find an electron in this region of space. So n takes on the values of whole numbers starting with 1, 1, 2, 3, 4, all the way up to infinity. So if I'm asked, can n equal 17,426? Yes, it sure can. Can n equal 3.14? Nope. Whole numbers only, starting at 1. As n increases, the distance from the nucleus we expect to find electrons increases. And a little figure left over from the Bohr hydrogen atom, positive charge in the nucleus in the center, electrons in some wave-like fashion out here. Maybe I could say that this is the closest we would expect an electron to be most of the time. I would call that n is equal to 1. When we go ahead and give this some energy, as in the hydrogen lamp, and the hydrogen lamp has definite transitions, the electron goes farther out. So I'll go ahead and indicate that the electron is going to a higher energy state. N is equal to 2. I'm going to do one more of these to indicate that this distance from 1 to 2 on the board indicates some energy. From 2 to 3 is not this amount of energy. We would find the electron closer and less energy to promote an electron from 2 to 3 than 1 to 2. Let me go ahead and label this one 3. And if I were to continue with 4, 5, 6, go out to infinity, this converges at some point. Because we go out to n equals infinity for the principal quantum number, doesn't mean that we're an infinite distance away. This is a function that converges. Quantum number 2 is L. We often write L as like a cursive lowercase l. L is going to tell us something of the shape of the region of space where we expect to find electrons. We call this region of space an orbital. An orbital. L has some defined numbers. Before I write any function up on the board, let me tell you that L is dependent on n. So we usually go ahead and find out what n is first, and then figure out what L can be. L starts at 0. So it starts lower than n. Lowest value for n is 1. L starts at 0, and it's whole numbers. And in theory, it can go all the way up to infinity. So we could have L is equal to infinity. But L is dependent on n in this way. L can never be equal to n. It maxes out at 1 minus n. For example, if n is equal to 1, L can only be equal to one value. What would that be? 0. You can't have L being equal to 1 because L has a maximum of 1 less than n. When L is equal to 0, we say that our orbital has a volume of a sphere. And I have some models here, and there's some nice animations in the textbook. So these wires are holding the sphere up in the air. So the wires are not part of the model. They're just there so the sphere doesn't fall down to the table. At the intersection of all these wires, center of the sphere is the nucleus where the positive charge is. And this is the region of space, spherical, where we would expect to find an electron. And we say things like, there's a 95% probability that the electron is in this region of space. If n is equal to 2, L can take on two different values. So what are these two different values for L? If n is equal to 2, L can be equal to 1. It maxes out at 1. But it can also still be equal to 0. So we could have ourselves a sphere here. We have a new value for L. When L is equal to 1, we have a different shape. Many people refer to this as being a dumbbell or a bow tie. I refer to it as a peanut. So I'll hold that there, and it's as though you have two of those little nuts in the shell. And so when L is equal to 1, we have a shape that I call a peanut. The reason for this, why do I call it a peanut? It's historically incorrect. The P stood for principal, as in a principal line that they saw in a spectrum, but P stands for peanut, and we often use abbreviations like this is a p orbital. This is an s orbital. Sphere, S for sphere. So underneath sphere here, let me go ahead and put in quotes. We'll use an abbreviation for the spherical orbital as an s orbital. And for these types of orbitals, these ones that look like dumbbells or bow ties, I call them peanuts, p orbitals. We can keep going up. When n is equal to 3, L can take on 3 different values. L cannot exceed n minus 1, so we have to stop at 2. We have ourselves, for this case, a sphere, a peanut, and now we have a new case where L is equal to 2. When L is equal to 2, we have these types of shapes. At the center is the nucleus, and we would expect to find an electron 95% of the time in these regions of space. We call each of these a lobe, so there are 4 lobes here. Let me hold up the models. The models look like this. Here's one region of space where we'd expect to find an electron. Here's another that looks very, very similar, but its orientation is 90 degrees off, and it's supposed to be put on top, overlaying there, so things get rather busy. There are some others that look similar, and they're in this plane, and they're twisted like this. And there's a fifth, and it doesn't look like the others. It almost looks like a peanut with a little donut around it. Mathematical representations tell us these are equivalent in energy, even though they look a little bit different. So there are 5 of these. We call them, well, take a look at the shape, dragonflies. You could call them a 4-leaf clover. I call them dragonflies because I needed to come up with a word that starts with the letter D, because we often call these the D orbitals. Let's do one more. When n is equal to 4, L can be equal to 0, 1, 2, and 3. That gives us our new case when L is equal to 3. When L is equal to 3, we get 7. You can have a look at your textbook and see the representations of the 7. And they look like the D's, where you get 4 of these lobes, except there's a total of 8 lobes. And 4 of these lobes are coming out at you, and 4 are going back into the board. So I'm going to put some shading around here showing as though there are 4 lobes that you and I are being shielded from and can't really see that well. And there are nice airbrushed photos in your textbook. Now these are called the F orbitals. They went ahead and started alphabetical order, so for L equals 3, we have the F. If we were to keep going, we'd have L is equal to 4, we'd have G, and so on and so forth. I don't really know what shape to call this. It looks as though there's a dragonfly coming out and a dragonfly going back into the plane of the board. So, from the quantum numbers, we know the distance away from the center, and we know their shapes. There are 2